In this venue, I'm sure we'll be out. All the things we're doing together. I want to see that. I did. Did you get it? Okay, so let me, I'm gonna get the. Is this you here, Gordon? Yeah, it is. Okay.
First, Chris. Everything good, brother? I was checking out, make sure we're all back up and online. I stopped the broadcast for the reason I was But they, I mean, it's great because they give you 8 hours. They give you 8 hours. When you put an archive on, and he wants the raw file, so I have to download this. Instead of cutting it up individually.
It's a little
Save us that, yeah. Yeah.
Do all the cut and slicing.
Yeah. Okie doke. I'm interested to see if you just okay.
You want to use the pointer?
I'm going to. Is it a click?
Yeah. Okay. Okay. Here you go.
Does anyone need it? Here, I'm gonna put my stuff right here and just put it over here so we get to it. So I have to click it once we're going to pointer. We're just gonna keep this on. Sure. Oh no, I am going by.
Yeah, where Matt is.
I think you're talking to move. That's good. I'm gonna stand.
Whatever you do, whatever you do.
Hey, Chandler, you get it like.
No,
I think actually it might be set up for the day.
Hello.
It's not loud.
Does it work? I think it's good. Yeah.
Sound good?
Yeah.
We can always done our hand done. Yeah, we can always do it. We can always do it on the move.
I can't see it at all.
Oh, no, that's
Yeah, right there. I mean, I wonder if the light will actually work.
No, it's a light.
So what's your time? Yeah, take time yourself.
I told him to put it away. Yes.
Because he can. Yes, sir.
Stay to the side.
Adrian? Remember the match for, they're looking to keep it on just for reliable purchase.
Where is
Oh, I didn't know whether you needed that with a laser. From which customer?
We could do it like.
Specifically designed not to reflect light.
We could do like.
Yeah.
And then roll it up here, on the side.
They're looking for.
I think we set it up for next time. Okay, guys, why don't we go ahead and get started?
Are you standing like this?
Okay. Because supplementary design, yes. Because we're the ones that should have seen that shit up.
I think that one.
I don't know.
I thought there was one there, and I thought I might have working.
Oh, they want to know the terms around the drawing.
Okay, thank you very much. Appreciate you coming back for after lunch. The next group that we're going to have go is also focused on the pipe roller. They had a little bit of a different assignment.
Okay. Hello. We are the Pipe Roller Digital Displays group. And we were charged by EA Fab to figure out what the digital displays on the pipe roller machine meant. So our problem was that EA Fab has this machine, but it was bought years ago at an auction. And from what we've gathered, it was made in the late 1900s, and it didn't come with a manual when EA Fab bought it. And so pipe bending as of current is mainly guesswork done by the workers at EA Fab. To go through the process of how we try to come up with a solution, we first started off with methods in order to redefine and to actually figure out what we needed to do. And then we moved from there to researching the company and the machines and what it does specifically. And from there, we went to data gathering. So numbers, what the digital display showed when, for instance, the roller was at a certain position. Another method we tried was graphing and plotting. So we used a program called Logger Pro to try to figure out what the roller's positions meant. And lastly, we tried mathematical calculations using geometry and using like math in general.
For this this task that we were assigned to, we adopted the Luma School of Thought, which is based off the idea of human-centered design. And what it really did for us, it gave us a variety of tools and methods that help us generate innovative solutions. And this can be used, for engineers, marketers, economists. That's really why this concept is very powerful. As you may know, our problem is very mathematical based. You're gonna find out that in a minute. And as our project went on, what we really discovered is that our problem was surprisingly human. We weren't hired by Mr. Kuroga to solve this equation or derive this formula. We're here to help the operators of the pipe roller machine. So that being said, the appropriate methods that we use were interviewing. We spoke to Ball and Paul, the operators of the machine. They give us great insight and evaluation of the pipe roller and its current condition. And what we really learned about it is how integral the pipe rolling process is in the manufacturing process at EA Fab. But yes, it's very tedious. There's a lack of technology, or lack of better word, automation in the process. That's really where we come in. So the first day we were there, we did a lot of data collection, a lot of learning, and 90% of our work was just being there on that first day. We learned so much. You'd be surprised at how much you learned from just looking and listening. We went further to develop a stakeholder map. Next slide. We plotted down the stakeholders and this in the arena of this general situation. And what we learned from this is basically, how do we make this process more efficient, and how do we help out Ball and Bob? I'm sorry, I just mixed up the consonants. Bob and Paul. And obviously in any manufacturing process, there's multiple steps. So after the pipe roller is welding, so we were thinking, I apologize, I'm so sorry. How could increasing the efficiency of the pipe rolling process affect affect the welding process, concurrently, because you're as fast as your slowest process in the production line. And we came to a general conclusion that pipe rolling was the most limiting process in manufacturing. We also used a concept poster, and what it did for us, it helped lay down our ideas. And a lot of times we got to like a dead end or something, and referring back to our concept poster really put our problem back in perspective and planted fresh ideas in our mind. So The Luma methods were essential to our project. I just want to thank Bill Lucas for introducing us to that methodology. Thank you. I'm Alex Galamus. I'm going to be talking about the machine itself. And this particular pipe rolling machine was created and built by the Birch Metalworking Group, who is now owned by MegaFab. The model of the machine is the Century 2 and is estimated to be at least 40 years old. It's a very old machine. And the pipe roller was bought at auction from the Metal Fab Machinery, Inc. When the machine was bought, there was a lack of instructions on how to operate the machine, as well as no records of previous ownership. And this presents great difficulty for the operators, as we know already. Because of its age, it performs very basic operations, but with little accuracy. This is the pipe roller machine itself, and on the left is a picture of the machine. And on the right is a picture of 3 die. You can see there's one hidden in the back of the picture. But these 3 die are used to bend the pipe itself. The machine was actually intended to be an angle roller, but the dies were swapped out to be able to bend pipe. These 2 die, the back 2, this one will stay stationary. We'll move on an axis, either in or out, to accommodate for the diameter of the pipe, and the other will stay stationary, like I said. These are the digital gauges used to measure the displacement of the hydraulics used in the machine. The gauges on the right are broken and were replaced with the new digital displays by the previous owners. The gauges on the left represent the linear transducer displacement for the hydraulic system, and the numbers can range from 0 to 10. There we go. These are the pictures of the linear transducers themselves, and basically what they are is it's a fancy way of saying displacement ruler. And what this device does is it measures linear positioning. In this case, it measures the displacement of the 2 mobile die on the machine. And like I said, these values can range from 0 to 10 that are output on the digital display. This is a brief video showing the movement of the die itself. As you can see right now, they are currently moving back on an arc, and they also move.
The one on the bottom is stationary, the 2 on top are the 2 mobile ones that generally are symmetrical alignment.
And these will also move forward in that same arc path that you see there. And these are our approaches. Our first approach was to use geometry. And for this approach, we used known dimensions of the machine and derived an equation that attempted to develop a radius for the pipe using transducer values displayed on the machine. For the second approach, we graphed the movement of the rollers on a program called Rocket Pro by using our equation and known dimensions. And we were able to show the movement of the 2 die to hopefully find a relationship between the 2. Our third approach was to model the machine itself in AutoCAD. And we used this program to model the machine and create an image of the outcome. The fourth approach was to contact MegaFab, the auction, and hopefully acquire any information we could. But unfortunately, no information could be found because of the age of the machine. The fifth approach was to contact Metal Fab Industry, which is the auction where the machine was purchased. I tried to seek out any records of previous ownership or any original documentation of the machine itself, but because of contract complications and the age of the machine, I was unable to uncover any other information.
So now we're going to go into a little further depth on what Alex just talked about, the first 3 points. I'm just going to start off by doing the geometry part. So what we did was we made this drawing here where these are the 2 dies that move, and this is always a stationary die. And we tried to find a relationship between the distance of these 2 dies and the distance between the stationary and the moving ones. Keeping in mind that in all cases, this distance between the two moving ones and the center stationary die, these should be relatively the same whenever you're using the machine. And so there was a lot of Pythagorean theorem geometry that we learned a while ago. So it's coming back. And we eventually got to this equation over here. It's long and ugly, but it is, it is the correct representation of the radius in terms of the distance between the two dies and the distance between the stationary die and one of the dies. Now, we didn't have any way of yet once we found that this equation, we didn't have any way of relating the distance between the dies and the gauge values. So what we did there was we literally got on top of the machine and measured every time the gauge moved one half of a value, we measured the distance, and we used regression in Excel to come up with these, which they look pretty nice. Unfortunately, the unfortunate thing about the geometry though is there was an extreme uncertainty, because whenever there's lots of multiplication going on up in here. Whenever, say you have a value that has an uncertainty of 1/10 of an inch, when you square that value and multiply them together, that uncertainty of 1/10 of an inch jumps to 1 inch. When you add them together, that goes from 1 inch to 2 inches. And it keeps accumulating and accumulating until we found that this equation right here had an uncertainty of about 5 inches. When we're dealing with tolerances of 1/16 of an inch, that doesn't work too well. That won't be very helpful. So this method right here largely was just too inaccurate to become of much use to Paul and Bob. So we then went into further methods of looking.
So the next method we tried was using Logger Pro, which is a program where you can videotape moving things, and then as long as there's a scale, it will be able to plot the positions of the things that are moving in relation to a stationary point. So what we did was we went to EA Fab one day, and we videotaped the movement using a few of our cameras, and then we plugged it into Logger Pro. However, we found that the positions and the values that we got were not very accurate because the camera was unable to catch all of the movements. So here's what we got. The first graph on the left is the movement of the top roller, which is if you look at it from the top, and the stationary roller is up. Then we're looking at the right roller that's moving up and down. And so those values were pretty decent. However, the bottom roller, yes, the other moving roller, we were only able to get maybe 2, 3, or 4 points. So in general, we weren't able to find out any relationship between the digital display and the movement of the rollers.
So after those 2 attempts trying to use Logger Pro and geometry, we decided to go into AutoCAD. I drew this tiny picture to ask Bob and Paul to take on that side, brother. I asked Bob and Paul to take these measurements from me, and when I did so, Pedro ended up going on a plane, and he decided to look at these measurements and help us with the math and try to find the exact distance between what was crucial. So we have the distance between these 2 points, which are the same, which means it's an isosceles triangle, which after a lot of math, we were able to find the stationary point, the stationary roller, the central axis, which is the center point of the 2 moving rollers. So after that, I drew an AutoCAD. So you have the two moving rollers, the stationary roller, onto this moving path that they both move on. So this is the engage point. This is our default. This is where you can put the pipe in between these 3 rollers, and the pipe will be completely 180 degrees. It won't have any bend in it. So, and then with the other measurements, I made the pinch point. This is half of it, but it's zoomed in. So it is when this moving roller is completely touching the stationary roller. When this happens, When you put a pipe in, it will go wrap around this stationary pipe, giving it a diameter of 7.5 inches. And yeah, right. Yeah. This is an ugly picture. It kind of looks like Mickey Mouse. But if you go into the program itself, these are 40-ish points, 44 points exactly. When this moving die is moving down 1/16 of an inch, because with all this geometry and all of the log pro data being inaccurate, we decided to just give them stepping stones. So I tried correlating the digital display every half a value, so 10, 9.5, 9, to the moving spots, and then I pretended like I put a pipe here touching this point of contact. I drew a line from the stationary to this center point, which showed the point of contact on moving rollers, and then I drew the pipe in itself. But after that, it turned out to be, after a few points, I started to get very inaccurate. I don't know what happened. I tried going over and over again, but so another method we did is similar machines. Similar machines, so throw away the one you have right now. It's a straw. It's a lot of work. About an acre. So this is one of them. Possibly looking at different machines. There's this one company called Pack. There's a few machines that are very similar to the one you have right now.
Okay, so we looked at the entire line of Pack APKs machines and their pipe rollers, or they could also be angle rollers, but we can replace the dies with the pipe rolling dies. And so the APK81 was the one that's that was the smallest and the least costly, that also we think would be able to accomplish what we need to do.
It would be able to roll the 2/7/8 inch pipe, just a pipe. It wouldn't be able to bend solid. This is the big boy. This is what you want if you want to do everything. If you want to bend 5-inch solid pipe, you can do it in this machine, but it's very costly. And so this is what you want if you want to do anything.
I don't think their pockets are that deep.
I agree.
So
Create completely.
Well, you're gonna have to spend a bunch of time on the gauge to make up for that.
okay. So the solution, going back to AutoCAD, is I showed the distance between the moving rollers and the stationary one, which is the values here. And then I showed the radius here of the inner, so as it's touching the stationary, and then the central radius and the outer radius, and the correlating displays, which is a stepping stone of 1/16 of an inch between each of these. So if you look at your sheet and have to get whatever it is, you look at this chart. But it only goes for about 24 points, and it becomes obscured, and it did not look well. Yeah. But that is our solution.
Yeah, so I'm kind of here to conclude in saying that it is almost, we found near impossible to find the radius given those display gauges for multiple reasons. The first reason being, when we first went and we were playing with the gauges and testing everything out, we noticed that even the gauges themselves didn't fit the machine at all. They were separate. They're separately made from the machine, right? So when we're looking at this thing and you guys were trying to zero it, and you're like, we got it close to zero, is what we said. But when they're doing this, inaccuracies of up to 1/16 of an inch, close to zero isn't gonna cut it for you guys. So the gauges themselves are inaccurate. Then talking about just having all of these unknowns and getting so much geometry to work ideally causes more inaccuracies, because this is the real world and geometry doesn't work like that. So not a lot of our data was found to be useful, because we're convinced that we've been working on this problem for a couple months, and we think that it is not entirely possible to find it accurately with the gauges. So even though we might not have the best solution, with those gauges, which is what also we looked into, is finding other gauges, but we found that we wouldn't find much of a different problem if we just got these gauges, right? Because they're not for the machine, they're not inherently in the machine, so you still have that zeroing factor of close to zero, not close to zero, and just that it can't be accurate. the way it is right now. So this is why we suggest that you take some of the values that we have found in AutoCAD and test those against what you guys do know, and also investigate further into looking into machines that have gauges that were meant for those machines, because the gauges that are on these machines are not meant for these machines. So do we have any questions?
So the moving rolls displace, you're saying hydraulically?
Yes.
Our radial path.
So you're trying to move, so you're trying to judge the amount of displacement by judging the amount of the displacement of hydraulic fluid? Is that the thing you're measuring?
No.
No.
All right, so the linear transducer, what it does is it has basically, it's got like a string on it that is attached to the rollers that moves whenever you push the hydraulics forward and move the die forward. It pulls on that string and that moves the thing that measures it.
It's moving along an arc.
It's moving along an arc, and the linear transducer is also linear.
Yeah, the transducer moves linearly, but the thing moves radially.
On an arc path.
Yeah, so we regressed that and we got some crazy function that's not worth your time. We also, we probably should have mentioned the solutions. We were thinking about possibly reconnecting the end of the string to the middle column of the center axis, so it comes off tangentially. So you would get that linear relationship that could make the mathematics less easier. But one less degree of freedom, and therefore you get one step. The certainty that's within the accuracy that you want, but it would not solve everything. Yeah. So we thought about moving the transducer as well, but we found that that it would be almost the same, because we did when we practiced the equation to see just how far off it was. We didn't actually use the regression models. We just literally got on top and measured it again to see those distances, and it was still off by 4 inches, which is like 900% error, something like that. So.
I just want to say that this is by far the most challenging problem of them all. I mean, in paper, it does not look like, I mean, it's one of those problems that it doesn't look that appealing, but mathematically speaking, we are in the presence of the top 1% of the top 1% of the industry. I mean, I can tell you that when we started, to do this thing, you can end up with a formula this long, this long, this long, this tall, this wide, and it is an application of tangents and law of tangents and narco science and all the different stuff that
we don't do calculus as well. And whiteboard just every day. We're the last class of the day, so our brains are already frying and push.
I can tell you that I'm very proud of what you guys have done, because this is something which we know it's impossible per se, because we haven't figured it out.
Something inside now.
We know that it is by far very challenging. We have to have a way of measuring this thing way more accurately than it is right now, in order if we want to try to use those gauges. I went to a shop in Mexico about 3 weeks ago, and they have that APK with the big one, the big boss, you know, and they do have their displays too. And I went with the man, you know, not with my partner, but with the man who operates the thing. And I said, obviously there's not little display, so why do you use those for? So why do you use that thing for anything? That's what their response is. And the APK. I mean, there is so much that has to be done in terms of design. If you guys end up going to a design career, this is one of the main things that I told you, that this is an industry that is in diapers in terms of accuracy. There is 100 million things that still have to be fixed. Just sure, there is a solution. But there is a solution, and that is a challenge for you. I mean, it's just one of those things. Those particular things, remember, that machine is from 1950, whatever. 84.
We found, we dated it somewhere.
But the design is from.
Design, yeah, design is,
you know,
Christopher Columbus.
correct. And, and that thing is, those were gauges that were bought at the time, trying to replace some manual gauges that still didn't mean what, you know. So the diligence of this case has shown, I was in an airplane and I started to get all this math, and then the guy next to me, he was trying to like, "Hi, my name is Elena." I was like, "I'm sorry. I am doing all these things, and I filled out my tablet full of all kinds of different formulas, and one day I actually came down with Ryan that said, like, "Hey, try to follow this and see if I got anywhere," It is, and it is a great problem. It's one of those big challenges. I don't see this as a bad thing, actually. It is a general conclusion and an open-ended project for the next time, because there has to be a way. There is a mathematical solution. I am convinced of that. The question is this the right equipment to try to test it? Either the gauges, either the way.
Mr. Pruitt, I'm sorry to interrupt you. I was saying you should probably maybe investigate the potential use of lasers or ultrasonic sensors to measure distances.
Sure. Now, important that they have a 5% margin of error on the laser.
Yeah.
And that's one of those things, and you're throwing your laser at a radio thing, where the laser needs to have some perfectly perpendicular to have an accurate thing. So there's a bunch of challenges. There's solutions that can be on the cylinder, on the hydraulic part, on the mechanical part, on a bunch of different things. And 7 weeks, it's a small time for me. So I really congratulate you guys for what you've done. It is not a bad thing. It is a lot of diligence that we have seen.
So the dies that you bend the pipe with, do those occasionally have to be redressed?
No.
So they just go for years and years?
Exactly.
And so if there's a variation, so what's the tolerance variance in the pipe itself? I mean, you can have perfect setting on the machine and two pipes will come out of different radius if one's to the high side of tolerance and one's to the low side.
Not on the other. The forming of seamless pipe, it requires that people basically you start with a solid piece of bar. And the piercing process in the steel industry, basically you grab, you grab 8 inches of solid bar. So it's about something like this. You heat this up to about 1400 degrees Fahrenheit, and you basically have a pinch. Imagine a finger that goes in and goes and right there through the middle, and you basically squeeze this sleeve in, pull it out, and that becomes what I call a shell. And then it goes out, and you have a bunch of different rollers that start stirring this thing. And basically, like you're doing pretzels, you want to do this thing, and then the dough starts, going longer and longer and longer and longer and longer. There's a lot of discontinuities on the inside diameter, the location, but the outside is the only thing that is mechanically formed. So you can trust that the outside radius or the outside diameter, it is round. No, it can be maybe 5 thousandths off on the diameter, and that is the part that we apply the pressure to. You have that's fine. Just scroll up.
Which product are you looking for?
The roller's view.
Output view of the roller.
No, the side view that Alex was showing. Right there. Number 10.
Transition.
No, that's what I'm saying. That's what I want.
Not that.
No.
No.
Number 8.
Like I say, we have a machine piece that actually conforms to the outside. And what it does is that the two rollers that move inside, it pinches the pipe and puts an initial bend. That initial bend moves it in and creates like a little V shape, which is not V, it's actually like a little curve. And then the hydraulic system goes out, locks in place, and then all the rollers start turning. You guys have the thing moving? Now, right now this is just showing the rollers moving in and out, but every single one of those will have either a gear or a motor that makes them all turn at the exact same speed. So all 3 rollers will start spinning, but no hydraulics are going in here, just moving. So that pinch that we created, it gets then transferred into the pipe. And you can hear where we're maintaining that little, like this. So now you are like this, and so when you start actually moving the pipe, you don't create a bender. That's why this is very important. This is not a pipe bender. You grab our pipe, and if you have a bender, you bend, and move it, bend, bend. You can create a radius like that. Bending, bend, bend, bend. But you see these little straight sections like that. This one rolls it. You roll in the pinch, per se, into the pipe. And that's what this, this water is doing. Even if there's a discontinuity on the outside, that discontinuity gets basically pressed back in place by having this roller. The one key thing, the material of this roller has to be a 41-40 material, which is about 3 times the hardness level of the pipe. So if something is going to deform, it's the pipe and not the rollers. If you make the rollers softer or weaker than the pipe, well, the pipe just brings the rollers back out of it. But it has to be heat treated, and yeah, and again, they share. Actually, you can see right there where they share the same center, the movement. And at this moment, we only have a linear transducer into it. The problem is that in this particular case, we're working with a fairly small radius, and a very small deviation creates a difference in the radius. That's why we need to have a gauge.
So we're running a little low on time, so we're gonna head out.
Any other questions for this group?
Any quick more questions?
All right, we'll give you an opportunity afterwards. Thank you very much.
Sorry?
We have one more group to go, and then we'll be done. So we have one more group to go. This group has designed a panel rack, a rack to be able to carry these panels around. And they brought the show and tell pieces.
Some places have our toys. So, good afternoon. Today we're going to be talking to you about the panel rack and our solution for that problem. I'm Brendan McCann.
Sarah Hertzler,
Chair Paul.
Emily Hughes.
Patrick Larch.
So without further ado, here's our panel rack solution.
So, AK Welder Steel, one of the Fab's customers, came to EA Fab asking them to create a rack which could store and transport the 6 various panels. The panels line the inside of the furnace, and water is run through the pipes to keep them from melting. However, after constant use, they do wear down and they do corrode. And when this happens, they need to be replaced. So rather than just having spare panels lying around the factory, a rack which can hold all 6 would be much more organized. So that's what we sought to do. We sought to create a rack which was sturdy, accessible, compact, organized, and transportable. Not only does it have to be able to hold the panels though and transport them, it also needs to be accessible to the panels so that they can be tested before they go into the furnace. Water is run through them to make sure that everything is in order.
So, as you probably heard, balloon methods, we use 3 different balloon methods, and they included concept mapping, rough and ready prototyping, and thumbnail sketching. So we created a concept map in order to get a feel for the overall problem. We know that EA Fab was making this for AK Steel, who operates their furnace frequently, meaning that they have to replace these panels a lot because they often corrode. There's 6 different types of panels, each of varying sizes, and we kept in mind the largest was about 6 by 8 feet. These panels each have different access points for water, so they're all very unique in their own way. And we wanted them to be stored not only compact and organized, but each panel needed to be accessible when still in the rack. And the rack itself had to be transported by various types of modes, such as a crane or a forklift. So you could move the rack itself, and then each panel from the rack would need to be transported from the rack into the furnace.
So, here, these are the presentations. So basically, one of the other methods we used was a rough and ready prototyping. And basically what we used that was to simulate all the different types of the panels. So these were all made to a 1 foot equals 1 inch scale. And it really shows a great representation of the various sizes we needed to accommodate. So we needed to make a rack that would hold both this and 4 other panels of varying sizes. So it really gave us an excellent idea of all the variables that we needed to consider when we were actually making a rack to hold all of these.
So we used math sketching to form our designs. So when we were given the problem and we used the limit methods, we took some ideas and we started drawing them out. And then we worked through inventor parts and then into inventor models to form 3 different key designs that we were going to present to Mr. Quiroga during our first brainstorming session with him.
So one of the first designs was the hexagonal design, and we have 3D printed some of these, so we'll just pass these around here real quick. One of the biggest pros of this design was that you could easily access all the panels from the direction. So you didn't have to move anything around. You could get to each of them depending on where they were situated. It was fairly stress resistant. So early on when we were going through this process, the stress analysis was very rudimentary because we just had done them as part files. As we proceeded through the process and narrowed our solution down, we ended up going to more in-depth inventor models that would actually involve framing, but Joe will talk about that in a little bit. So these very rudimentary stress analysis showed that it would hold up fairly well under the stresses there. It was 10 foot long, and they had those 10 foot long sides, and it had a footprint of 246.8 feet squared. So it was, of the designs, it had a very large footprint.
Another solution that we wanted to present to you was the toaster design, and I'll pass these around. The toaster design focused on compactability. It was inspired by a toaster or a bookshelf so that all of the panels would be together, neat and organized. And it ended up being 8 foot by 8 foot by 12 foot, meaning it only had 96 square feet of footprint. Again, it's very compact and accessible, and there are these 4 foot wide rooms in between each of the shelves. So if someone needed to go in and test one of the panels, they could walk in between the shelves and hook up the panels and use them. Again, we did a very rough stress analysis for this solution as well. The one on the top is if a crane were to pick it up from the top, it would initially have a lot of stress seen on that part. And the bottom being the panels hanging on the shelves below as it's hanging from a crane. We didn't know how to simulate the panels being actually mounted to the wall rather than just resting on the shelves themselves. So if they were to do that, it would have taken a lot of stress off of the bottom shelf.
Those are KSI.
Yeah.
KSI on the top.
Those were there when she was displacement.
Okay.
So our final model is the vertical hexagon model. Actually, this little model gives me a chance to talk about the 3D printing process a little bit. Unfortunately, when we printed our model the first time with the other 4 little models that are being passed around, we printed it in a similar scale, and the members of that model were a lot skinnier, so it didn't print correctly. This model, these are actually triple the size. Each one of these little members is triple the size of they would be on the real model, just so they will print correctly. And this black plastic you see is actually a filler plastic, so it can build vertically up And once you put this in a chemical bath, it will dissolve and you'll be left with the real model. So these are actually attached to here, so I'm gonna have to pass it around this one. So our hexagonal model, we developed it on Autodesk, like all the other models. What makes this one different is we got to use the frame builder tool. The frame builder tool is really, really powerful. It takes what may just be a shape, even just like you could take a cylinder or a hexagonal prism, like for instance what our model looks like, and you can use lines and points within the model to make frames. These frames are constructed of standard size members. In our case, we used 1x1 steel. There's thousands of choices. You can use tubing, you can use I, you can use T, just almost infinite choices. It's really, really helpful. This design actually came from an idea from a brainstorming session we had with Mr. Kroga later in the process. Here's some of our drawings from this process. This is kind of the rough, extreme beginning start of this hexagonal design. Just some of the features in there that you'll see are the base hexagon shape. It has the member coming up to be lifted from, similar to what our final design has. In that session, we also got to talk about yield strength and ultimate tensile strength. Those are critical to our model because, as Mr. Kroga, I cannot take credit for this, he used these words. It's like when you take a plastic bottle, yield strength is similar when you deform the bottle and it comes back. The ultimate tensile strength is when you deform the bottle and it's just destroyed. So we really had to pay attention to yield strength because we wanted our model to be strong and usable under the conditions we were given. So like I said, it's all 1x1 bar with the 6 half-inch plates underneath where the panels would sit. The footprint of this model is slightly bigger than the toaster model and a lot smaller than the other hexagonal model. It's around 160 feet squared. This model would weigh 18,150 pounds, just steel. So it's very heavy. We would have to be cautious of that and maybe reduce the weight somehow to use on a forklift. But with our model right now, that's the weight we got. Another powerful feature Inventor has is stress analysis. Brendan will talk about stress analysis in general in a minute, but for our model, we decided to test it in 5 different scenarios. The first of which being if the model was lifted by a crane from the top, full of 6 panels, one where it was sitting on the ground with all 6 panels, one where it was being lifted by a forklift with panels on either side of where it's being lifted, one where it's being lifted completely empty, and one where it's hanging with 2 panels on either side.
So when we went about actually doing this analysis, we're going to use the hanging example just as to run through. So one of the first things we had to do was actually constrain it. So we needed to figure out at what points there was going to be contact and what points would be free to move. So in this case, since we were picking it up from the top, we decided to constrain the top portion because that was what was going to be stationary and what would in general not be moving. And that was where our main contact was. The second step we had to do was actually apply loads to the model itself. So in this case, first of all, gravity was going to be one of the forces in the loads. So the object itself had its own weight that would be pulling itself down. So that was one thing we had to consider. In addition, since we are trying to hold the panels, we needed to apply forces for each of those panels. So we applied the forces for those panels down on the bottom where they would be sitting. And then, of course, we ran the model.
So to talk about the results with our model specifically, for this hanging analysis, some of the results we got were that it's actually a very, very safe design for the amount of weight we're putting on it. Some of the things we found when we were running stress tests that were really misleading is, I'm not sure if you can read it, but in our design, it actually has a maximum of 364. Yeah, that's correct. The reason that is misleading is because when you miter 3 pieces together, sometimes if you're joining at a right angle, you have a piece coming in from the top, and you miter them, it miters one of them down to a point. And the problem with the mitering down to a point is if you apply a weight to that point, it over concentrates it and it goes wet, it just explodes. So you could get a reading of like 1500 KSI, when in reality, the model itself is only experiencing around 5,000 if you ignore the miters on it. So that was something we had to pay close attention to in our models. We constantly were going back and fixing our different joints within our models and looking at the results overall afterwards. Part of our project that we're actually going to give to Mr. Kroga is we generated a report from Inventor with all 5 of our different tests in it and our actual model on it, which I'm going to give to you now. So, thank you. The only reason I chose not to display this report to everybody else is it's 302 pictures. And it's a lot of technical statistics, but it was really awesome experience. It's a class to read through. So our results is, with our different models, our safety factors were actually really high, which we're very happy about. When it was sitting on the ground, 55 times. So you can basically give this rack a load 55 times what it currently had on it, and it would still be safe. And this is comparing it to the yield strength, not even the ultimate tensile strength. So this would be safe to deform even a little bit past this 54.5. It may not come back after that point, but it's still not going to explode, basically. So any questions on our design?
Two hexagonal designs, and one of them was considerably fewer square feet than the other. What was the difference between the two hexagons?
The difference between the two hexagons is on the model that Brennan presented, the hexagon actually angled to the top. And the reason the footprint was so much wider is because the top hexagon had to be as wide as the widest of the panels. Therefore, the bottom hexagon actually had to be a lot bigger to accommodate that, just the geometry of it. The vertical hexagon, both hexagons were the same size, so they could both be the minimum size, and the footprint was a lot smaller.
And there was something to keep them standing vertically.
On the bottom of that model, there's actually a little pocket, and what would hold the panels in place is we're still very new with Inventor. We don't have a lot of experience in Inventor. We would like to put a chain across each of the front of the panels to lock them in place. Mr. Krogan, again, in our brainstorming session, it's important to have it be safe so that somebody could unlock it or release it without having to reach far, just a very safe manner. So we thought chains would be a very good solution to hold the racks or hold the panels to the rack.
How much do the panels weigh?
They weigh around anywhere from about 13 to about 1,600 pounds. We also had to take into account any waste that would be left on them from the actual furnace, any water that might be left inside them from testing. In all our stress tests, we ran them as 2,000 pounds apiece.
On this last model, how will the panels hang? How will they be?
They'll actually be sitting on that bottom plate, and they'll just be held in by a chain. There will be 6 half-inch plates. Yeah, will be sitting in a belt.
So what are you guys doing when you graduate?
I'm still looking for schools. I'm waiting to hear back from Rochester University.
What do you want to study?
Either mechanical engineering or applied math.
I'm planning on attending Miami University of Ohio, and I have no idea what I'm going to major.
I'm a junior, so I haven't actually even gone on most of my visits yet. I'm going to be visiting Virginia Tech, UVA, a couple of the southern schools over spring break. I'd like to major in mechanical engineering.
I'm going to either Case Western or Embry-Riddle for aerospace engineering.
And I'm going to attend the University of Pittsburgh for mechanical engineering.
Along those lines, since I can't ask any questions about the technical part of this, has this helped you in your decision? I know you're not decided yet, but what you've done, has it really helped you, especially the junior, in what, thinking about your future?
I would have to say yes. I had some experience with Inventor in Mr. P's class my freshman, sophomore years. It was an intro to engineering class, and this actually just blew me away with all the new things I was able to learn. And I just really enjoyed the overall process of designing and building and just CAD in general, which is critical to be a mechanical engineer now. I've actually shadowed a couple of mechanical engineers who use similar programs. It was just really cool to be able to be using the same stuff they are.
Anybody else?
Yeah. So with engineering, it's such a broad spectrum of what you could be doing. And a lot of people, when they think they want to do engineering, they think it's just building stuff. And, fortunately for us, our project was building something. But, from the other projects, you can see that there's a lot of other types of engineering. And so doing a class where you're actually part of the engineering world and seeing what it entails really helps me personally to ensure that I do enjoy this and that is what I want to do.
I always tell the story for Southpointe administration, but all throughout middle school, I had no idea what I wanted to do when I grew up until I became a part of this all-girls engineering team my 8th grade year. So when I moved up to high school and I became involved with Mr. Garlick and his projects, it really solidified my love for engineering. And I've been a part of working with ALTAD for these 4 years and then working with EAFAB this year. And every time I do like a mechanical engineering based project, like I just fall in love with it all over again. And it really solidifies like what I want to do when I go to college. So.
Go ahead.
I just had one other question. From your perspective, how would you guys design, now that you've gone through this class, a collaborative class? If you had if it was the perfect world, how would you talk to your administrator?
No limits, time or money.
Thank you, Dr. Dudley.
Well, you know, in a perfect world, one of the big things would be being able to meet every day. That was one of the really difficult parts of this project is we have 2 different schools. Our classes only overlap for a short period of time. So getting together and collaborating can be difficult. So that would be a big thing is being able to work together basically every day.
I would have to agree with that. I actually think the class was really successful for its first year. I really enjoyed it. I wish I could do something like it again. It was really great to just, real world problems are huge for learning. I think it's just, it's not even comparable to anything that I've done in high school before. I'd probably say it's a safe assumption for the rest of us, but it's just, I think what Pat said was completely true about the time. I think the class really only needs a couple minor adjustments to be really successful again next year.
You know, one of the things that I think everybody's gotten from this class experience is that doing a problem that's an actual problem that the company has and is meaningful, it means so much more to us. We actually want to solve it and give a good product rather than a theoretical problem that we get in a classroom where we're sitting and just doing memorized calculations.
The question I have is for you guys as well as the administration. My son is a professor at the University of Bradford, majors mathematics, physics. And one of the things he's seeing a lot of is the students coming into his class are ill-prepared mathematically for engineering courses. And I'm just curious because I'm impressed with the depth of the mathematics that are applied here and a lot of the different solutions across the board for all the students. And so that's a great job for the administration here. But I'm interested in do you feel that you have the tools and the knowledge mathematically to succeed in the engineering field? Do you think you have enough?
I would say that at our high school, it's really kind of your choice how much math you take. For example, I've been a year ahead in math since I was in elementary school. So currently I'm taking calculus as a junior. Really, that's a really great math class to get you started with engineering. However, if you weren't really interested in taking math classes, you could stick to the absolute minimum and take regular FST as your last math class, which is a pre-calculus class. So I think if you really want to be prepared, then there's plenty of options to get you prepared for it.
Yeah, and we also have a great physics class. We have 2 different types. We have AP Physics 1, which is more of a basic physics class for majors other than engineering. And then we have an AP Physics C class, and it's both mechanics and electricity and magnetism. So you're definitely prepared well if that's the path you want to pursue.
To that extent, even just having, as Joe said, calculus, because that is different from any other type of math you've ever taken. And that is definitely, along with our problem solving, even what we're doing here, it's all about problem solving. So especially in that levels of math, our teachers always saying you got to get creative. So definitely getting ready for that level. It's taking as much calculus as possible in high school
One more question for these two.
Well, I just wanted to tell you a little story because it just so happens that last week I was at Autodesk, talking to one of the executives, one of the senior strategists, and sits next to the chief technology officer and the senior leadership and education division. I wish I could transport you so I can see what you're up to. They'd be thrilled. And one of the things, I just gives you a little, I'm not at liberty to tell you the stuff that we talked about, but the little hint that I can give you that's really interesting, just to kind of tie a bow on a lot of what the themes have been running through the whole day here, is that they're really leaning into, in the future, they're really leaning into this mindsets thing that Dr. Allen was talking about. What they're really leaning into is beyond just equipping people with technology to make these incredible models and become concept. They're not going to make that go away. That's going to, and your point is really well taken. But they're really kind of getting to the qualitative stuff. That's the red thread running through all this kind of stuff too. And we had a really interesting conversation about the Vitruvius. Did you see the Lego movie? Yeah? You haven't seen it? Shame on you. Come see it. Don't go to class. Just go see it.
Go see it in class.
Yeah, well,
That's why we only invite them twice a year.
but you learn more than that. There's a character in there. There's a character, the master builder, Vitruvius, named after Vitruvius, who was like the first architect, the main architect of the Roman Empire from 16 AD. And he laid down these top-level, time-tested principles of design called for commodity, fitness, and delight. That was the English translation in the 16th century. So fitness goes to your question. Strength, and all the critical math and everything that we're talking about here, right? Like, it's got to be stable. It's got to be structured. It's got to be the safety tests, all that stuff, right? The fitness, right? The commodity is accommodation. So the usability, and you have that as a criteria. Well, some of the people did, right? So that's the attentive, and that's where we get, especially when there's human users involved, which is so wonderful about the applications, the apps that we're coming up. So, and then the third one is delight, right? This is the aesthetics. And so it's what he's calling for is that's the golden triad, right? Time tested, 16 AD, all the way up to today. So I just wanted to offer that up, take that to you, because encourage you and all your colleagues to take that forward into the next part of this project and beyond. You're going to see a lot of interesting stuff coming from Autodesk that's kind of getting beyond just equipping you with free software to do the mechanical engineering thing and getting you into this human-centered design mindset. So I encourage you to take that forward with you as well.
Before I let you guys finish, from myself and Dr. Angelo and from Dr. Rondinelli, I want to thank these two guys. They were our hosts today. Mr. Allen. Couldn't ask for a nicer facility. They'll have us back. We're going to book these places several more times, I'm sure. It's a great facility. Also, after Claudia and Pedro have their final words, the students will be available for a few minutes before the buses out at their posters. So if you want to take a look at their large format work that they've done using some of the Luma methods and those things, students will be available. How did it go? Final words, comments from anyone from EA Fab? Thank you so much. We could have asked for 2 better partners this year. We hope you stay with us. We love working with you guys, and this is your first time, so what'd you think?
Oh, I'm loving it. First of all, I would like to get a little bit of feedback of this particular project. Very impressed, very impressed with what we have seen. It was very important to me that you guys had the opportunity to actually see an actual order. That means this is going to speak for me and somebody else. And I will build this, and I will provide it, and I will send it for the office because everyone will want to look at it. We have to tweak it. I don't know. And send something 18,000 pounds, like that. But we will have something that will fit, and it will do this thing. I actually invited the people, our actual customer, to come over here. Unfortunately, you had something that happens a lot of in steel mills, which is that thing that we talked about that actually gets the time. And that's why we couldn't be here this morning. He did send us a text, letting us know. But it was very important to me that every single kid in this, in all the projects, actually had the opportunity to touch the users, to touch the final person that will be having to deal with the solutions that they're going to make. over here. Going into this thing, I do want to make sure, I'm very happy to hear that you guys are going to be going into a mechanical engineering module. You will see the light. I got to tell you to the girls, I cannot be more pleased to see ladies that want to go into this field that is typically being run by men. I personally have, and I have said it in so many occasions, my next full-time engineer will be a lady. I want to have a different perspective, a different way of making squares. You know, I don't want to be, I don't want to leave the diversity of that level of thinking, you know, just because we're just trying to follow this thing. That doesn't mean that I won't hire a man, so don't get me wrong. You know, we will have the important thing that you guys need to understand is that over here, you guys have seen a lot of different things on yield, and we talked about ultimate tensile strength and breaking crap apart. Crap, I guess it's crap, not the other thing. But the important thing is that you guys remember that because at the end of the day, what you see in the screens, at the end of the day, are cartoons, are just comics. The problem is here. Do you understand? Do you understand what this is telling you? So you make the decision, and you are the ones that take the full responsibility of whatever it is that you're covering. The day that a customer sees you saying that will hold your panel and will not fail, that guy can actually go hook it up where you're telling them where to hook it up, and the thing won't fail. Now, you need to get there with experience, with diligence, and knowledge. So when you guys go to college, have fun, learn a lot. Don't stop learning on this thing. You guys are going to be learning a lot, even from the people that you have even least expect. Particularly the actual pieces, when pieces starts falling apart, and you don't really realize that how did he know about that, you know, or to keep this thing out of the blue sky to actually run. Congratulations to you. You know, it's been a great thing, and to the program, to the class, my absolute respect.
I am extremely pleased with what I saw today with everybody. It's amazing to see all the different projects. When we started this a few months ago, I was thinking, what kind of student do we give them? And it's only because the class is, you know, science and math that we only do. But anyway, we thought all about the different projects, and now that I see the solutions, I think that the kids actually were able to see a lot of different aspects and actually think different than the way that I think, at least in my program. That's what I want. So, and also, it was also in our small company, more eager to work, and it's just different energy that is talking to me. So, for us, was a great experience. I hope for you guys as well. So, we thank you, and hopefully we can do this next time.
Again and again and again. we have to catch up with some people.
You gotta get in line, right, Bill? And students have that option to continue to work on this in the fourth quarter. Again, from the teachers, Mr. Piskorski, Mr. Garlick, and myself, thank you very much. We can't thank you enough for the opportunity to provide for our students. Do you have any other questions for them?
Thanks, guys. Move to your table. Look at your
And so what you told me, and that's where he justified Congress, that's a job of development. So with that, always for this.
Right.
What happens is that we'll have a and so your final something around here, and this bounces up and we adjust the wrap around here, and you might open another.
I mean, imagine this, that's one.
And that's what we're trying to do. So Mac,
yeah, it's about 1 o'clock to 3. That's how we communicate.
So you're charged tomorrow.
one of those things.
If we're our London,